Hi, my name is Tovio Roberts, and this is another quick episode in latent topics in data science. Today we're going to be exploring images, and the way that we're going to explore images is just through the context of histograms. I think we're generally pretty familiar with histograms. I'm going to be applying histograms using matplotlib, pyplot, skimage, a little bit of opencv, numpy, related technologies. And yeah, a quick word on this. When you're doing image processing, often you'll be looking at histograms of images. You'll be looking at the histograms of the luminosity. You'll be looking at histograms of the red, green, and blue channels, or hue, saturation, value, channels, whatever encoding for the image you might be using. You're probably going to look at histograms of those channels at some point, because those will give you some insight into the image data, much in the same way as histograms give you insight into continuous data in any data set. So we're going to be thinking a little bit of images as being a type of signal, which is not often how people think about images, but that's how we're going to do it. And we're also going to be looking at pictures of cute cats, and we're going to talk a little bit about the implications in regards to using an algorithm for detection of, say, a person, or detection of a cat, or detection of an object through this lens of histograms. And I'm going to point you at a paper, the original paper on histograms for oriented gradients, or HOG as it's often called. And this paper is sort of a seminal work. It's really, I think it's important to understand how this machine learning algorithm came to be, and in light of where we are now in terms of face detection, pedestrian detection, object detection, and those kinds of things. But that's getting ahead of ourselves a little bit. I'm going to be working out of this GitHub repo, which I will put into the chat. It's also in the description. And I'll be updating this as we go in case you fall behind coding, if you're coding along, or in case you want to, just reference this after we're done. So I'm going to be live coding this. And if you've watched me before, I miss things and I make errors. So, be patient with me. I think we're going to aim for an hour-long episode today. I think we've been doing 2-hour-long episodes, and this is a relatively simple concept, but I think it's pretty fun. So I thought I'd cover it. All right. So first, let's look at these cat images, and we'll think about them a little bit. So, waiting for that. So this is a small image of a cat, and just waiting for preview to zoom in a little bit. There we go. Looks like it's likely a red point Siamese. Oh my gosh, this might actually be my cat. I think I may have put a picture of my cat in this image set. Okay, well, either way, this is a cat, obviously. Notice that image is sort of grainy, and it's a very small image. This next image, I think, will be a bit larger, yeah, and has a slightly better resolution. Still, you can see these hash marks and from the roster of this. So when we're looking at these, we can think about these as being arrays, right? This is there's a red, a green, and a blue channel. All of those are two-dimensional arrays, and we can look at those individually as being different light sources, and we're going to do that in a little bit. So I'm not going to open all of these, but we'll see them kind of in context soon. And I chose these images because they're all different colors, right? Like there's some gray and green in this one. That's kind of nice. There's some red and gray and white, and you know, this color, peachy kind of color. Yeah, I think this is going to give us kind of a range of histograms, and that's going to be cool. Okay, so we're going to start off. I'm going to do all my work like I usually do for these live streams. I usually do all my work in one file just so that it's in one place and you'll see it in one place. You can reference the code in one place, and I'll probably do what I usually do and work out of an if name block here really quick. So if name is main, then we're going to run the code that's down here. Okay, so we're going to be using a couple libraries, one of which, I'll just pull this up, is scikit-image. I'll throw that in the chat. I'll put this in the description afterward as well. This is a kind of a counterpart to scikit-image in some sense, and it gives you access to a lot of fairly easy to use functions in a very Pythonic way that you can use to manipulate images. This is not as common an image processing library as opencv. Opencv is widely used and is you know, available for a lot of languages, and is I would say it's an industry standard. I like scikit-image quite a bit because, you know, if you have a small project or you have a simple function like converting certain images, you have very low overhead and you can do just quick, easy stuff. It's really fun and easy to explore. So yeah, so we're going to primarily be using scikit-image for what we're doing here. All right. So one of the first things we're going to do is, well, you know what I'm going to do? I'm going to import I'm going to use the OS library to import some things. So I'm going to say from OS import listdir, and which is just a directory listing, and get current working directory. And those are going to come in handy. And what I'm going to do here is I'm going to print the directory. So I'm going to run this list directory command from the OS library, and let's see what the working path is. Well, we're going to do two things. Sorry, we're going to print get cwd as well. So we'll see the current working directory, and then we can get a relative path, or we can get a static path, canonical path, from which we can get the contents of our data directory. So let's run this. Let's run python histograms.py. And we're seeing two things here. We're seeing this is our canonical path, users, tbot, Dropbox. I put everything in a Dropbox for redundancy. And we've got this histograms for cat images. So if we look, this is the root directory, and there's a histograms.py ds store, which is you know, an indexing file for OS 10. Images, this is a directory, images, readme.md, and this .gitignore, which is preventing syncing certain types of Python files. So if I look in the images directory, I'm going to go ahead and comment this out, this get current working directory. I'm going to look in the images directory for our images. So I'm going to run this again. And notice this is cats 00172, cat 00011. These are all images from a data set that has cats, dogs, and pandas in it, and I just chose some random images out of it. So what we can do with this is we can put these images into a list, and let's go ahead and do that. So this is just going to be animals list, and go ahead and clear that. And I'm going to just print the length of the animals list. And we should see, well, we'll see how many we have. There's 8 in this, so. So from here, we can, well, you know what? Let's look at the contents of there, of that, because I'm suspecting that there's actually a DS store file in there, and we probably want to remove that from the list. Okay, well, it hasn't made that as yet, but it's a common thing when you're reading in images that you're going to, if you're on a Mac, you're going to, you know, get this DS store in there. So I'm just going to preemptively remove it. This is a kind of a common thing to do. I'm going to say if .ds store, I think it's like that, is in the animals list. Then I'm going to say animals list.remove, and I'm just going to remove that item. It's just a little cleanup, preemptive cleanup that, you know, if you're on a Mac, you're going to find yourself doing that. So I'm going to, what's a good way to do this? So if I print animals list sub 0, this is going to give us one of the images, right? Cats 00172.jpg. And what I probably want is a full canonical path. So what I'm going to do here is, well, let's do it like this. I'm going to say I'm going to import something from skimage. I'm going to say from skimage.io. I'm going to get this imread method now, or a function. So imread, it exists in MATLAB, in matplotlib even, and it exists in opencv. It's a very common function name for image read, right? So let's do this. Let's read in this image with imread and just see what happens. So I'm going to do imread of animals list sub 0, and let's see what we get. Okay, we're getting a bunch of errors, and that's what I expected. So if you look at this, there's no such file as, you know, in the histograms for cat images / cats underscore 00172.jpg. Well, that makes sense. We're not in the images directory when we're doing this. And a way to get around this error is we can append the current working directory to all of the animal list file names. And that's what I'm going to go ahead and do. So I'm going to say, let's go ahead and overwrite the animals list. And let's say, what's a good way to do this? We're going to use the CWD get current, the get CWD, or you know how we can do this. Yeah, why don't we do that? So let's do get, I'm going to do this. I'm going to say CWD, and I'm just going to get CWD. And here we're going to say let's let's do cwd plus, and then we're going to have a slash in there, not a backslash, but a forward slash. And this is going to be file name for file name in the animals list. And let's see if that works. I can think of a problem here. So this might not work, and if it doesn't work, I know why, and we'll get it to work really quickly. So if I run this, oh, it looks like it's going to fail. Yep. Okay. So why is this failing? Users, T-Bot, Dropbox, Galvanize, blog posts, Histograms for cat images. Huh. Oh. Interesting. Let's just go ahead and print out this animals list and see what's in there. For file name, animals list. Let's print the file name and just see. Okay. All right. Then I think what we need to do is just that. So let's see if that works. And okay, that looks like it did work. So I'm not getting an error anymore. Essentially what's happening is we're able to read in this first image, which is what we're going for. All right. So now that we have that read in, let's just take a look at it. I'm going to throw this into, let's see, I'm going to throw it into something called cat image, and let's print the shape of this. So this is going to be cat image dot shape, and why don't we print the type of it as well? So print type of cat image, and let's just see what this does for us. I'm probably going to move into IPython really quick here, because notice how much lag I'm getting when I run this. So this is reading in these images, or it's reading in an image after building the directory, and there's just some overhead in time. And if I have it running in IPython, I can take a quicker look at everything. So notice the type is an image.io.core util array. This is a lot like a NumPy array, and it can be accessed in a very similar way. And then we've got this, it's 499 rows by 411 columns by 3 channels. And that's sort of like 3 arrays stacked with each other, if that makes sense. So, cool. Let's print, well, I said I was going to go into IPython, and I'm going to. So let's take a look at this. Okay. All right. So I'm going to go ahead and run histograms.py. And we should be able to sort of explore. We should start being able to explore this a little bit more. So from within here, so I'm, notice I'm getting the same output. I should be able to look at cat image sub 0 sub 0 sub 0. Need And this is looking at, you know, the initial channel, and it's the top left corner of the initial channel of this image. And why don't I just open that image so that we can take a look at it. That would be this cat right here. And the pixel that we're looking at is somewhere, is way up here. It's this top left pixel. And notice that this is 159. So this is, you know, if this is RGB, and it should be, if this is RGB, then the red value up here is 159. So let's look at the gray value. And that looks like it is also 159. And that one also looks like it's 159. That's a little surprising. Okay. Why don't we look at an image? Oh, okay. That is not surprising at all because I'm looking at the wrong thing. Here, let's do that again. Say cat image. And so this might be a little more telling. So this top left is 159, and we're seeing the 3 channels, right? So why don't I'll look at cat image, and let's look at 0, 0, and then 2. So that's 201. So to correct what I just said, if we look at 0, 0, 0, that's the value of the red channel, which is 159. And the value of the green channel is 177. And the value of the blue channel in this top left pixel is 201. Now, something, if you're familiar with these color codes, they go from 0 to 255, and they're integers, right? 0 is black, and 255 is white. So if these colors are all close enough to each other, then they tend to be gray. And notice up here, this color is gray, actually. So that kind of makes some sense. We could take something, let's do something else here. Let's look at a color somewhere around here, and we'll just say cat image, do 50, 50, and well, we'll do 0 because we're on the red channel. So that's 151. And then let's do the green channel. That's 164, 183. So that's sort of a different gray that we're looking at somewhere in here. If we were to grab one of these, and we'll look at this in a different way shortly, but if we were to grab one of these colors would be, these values would be much lower as it would turn out. So, okay. All right, so let's look at this image. And to do that, I'm gonna go ahead and do I'm just gonna add in some more code here. I'm gonna put my terminal back over on the left. And we'll stay in IPython. To get into IPython, if you have Anaconda installed, just type IPython. And I'll also, actually, I'm going to exit out of here really quick and sync. So let's do, I'm just going to push this, and then I'll go back into IPython. All right. Let me just pull pull that up a little bit. And I'll clear it. All right. So we're here. I'm going to import matplotlib now. So I'm going to say import matplotlib.pyplot as plt. And this is going to allow us to visualize this image. And to do this, I'm going to write a function. I'm going to write a visualization function. It's just a plot image function. So I'm going to call it plot image. And I'm going to pass in the image, and I'm going to pass in a title. This will actually be the title of the image, and that will help us just to identify it. And I'm just going to create a figure and an axis, and define these subplots. And let's see. Set a figure size. Do 18.6. Okay. And okay. And now I'm just going to show the image using IamShow, which is not an skimage function. That's a pyplot function, right? Pyplot. And this is how we're going to be able to see the image. So I'm going to do image, and I'm going to set the CMap to gray. So this is going to give us sort of a luminosity view. If we look at the red channel, we're not going to see it as red. We're going to see it as a single slice of luminosity values between 0 and 255. So where red is least contributing, we're going to see black or dark color. Where it's most contributing, we're going to see really light colors. And that's if we pass in a single slice of the image. But with all three channels stacked, we're going to get an output that looks like the original image using CMap gray. So there are different color maps, and you can use them for different reasons. Some of them can be really helpful in other cases. I'm going to stick with this color map because it's going to give us something that looks familiar. So I'm just going to set the title. So set title, and we'll just the title we pass in. That's going to be that. And just going to go ahead and do that. All right. So if we do that, we should be able to just pass in this cat image. So I'm going to go ahead and plot the image here. And this is going to be the cat image. And I'll just pass in animals list sub-0 because that is the title of the image. And I think that's good. I think that's what we want to do here. And if I run this, let's run histograms.py. Oh, matplotlib has no attribute subplots. Huh. Interesting. Figure x1, plt.subplots. Oh, sublots. Right, there we go. Let's try that again. And there we have an image of a cat. And this is not the cat that I expected. I think that this must not read them in the order that I expected. So that kind of explains some of the color stuff. Okay, why all these colors are the same. Cool. Well, here's a cat, and we can look at it. And if we were to look at the color at 50/50, we can actually see in this bottom left, it'll show us the X and Y values. So if I navigate to 50 and 50 up here, this color would be the same as this color over here. So let's try 209 and 171. So if I look at, bring this over here, gonna put this cat over here, and let's try to, again, kind of look at these colors. So cat image, and let's do from the red channel, we'll do it's not showing me the overview anymore. Well, that's okay. I think it was something like 170 and 250 or so. And we can do that again. 81 and 65. And that's a darker color. You know, we're looking at this 80, 81, 65. Those are closer to 0. All right. So we can view an image now. And let's kind of build this out a little bit more. And we're going to do this sort of in stages. And I think, you know, I'm going to code this out and we're going to get to something that works and will be helpful for viewing these things. So I'm probably going to switch over to a Jupyter Notebook in a little bit and import this file for that for use with that Jupyter Notebook. All right, so we're going to import some more stuff. We're going to import NumPy, and we're going to import Seaborn, just because it's nice. And I'm going to import something else from skimage. This is going to be from skimage.color. I'm going to import a function to convert red, green, blue to gray, and that should be all we need. All right, so we plotted the image. Now, you know, when we're talking about this, we're talking about red, green, and blue, right? But we have yet to actually split these images apart, and I think that's going to be important. That's going to be one of the first things that we want to do here. So why don't we go ahead and do that? Why don't we write something that'll split an image? So I'm going to write def split layers to 3. I'm just going to split to 3 images, and I'm going to use im for image, and I'm going to return a few things. So I'm going to just take this image, and I'm going to do that. So I am taking each channel, and I'm going to say for channel in range of 3. There's 3 channels. This is going to return each channel. So it's going to give me a list. Each list is going to contain a channel. So if I run this on, so I'm going to take split layers to 3. I'm going to run this on the image. And let's see, this is going to get R, G, and B. I'm going to print R.shape, G.shape, and B.shape. So we'll do that, and I'm going to run this, and then I'm going to open a Jupyter Notebook so that we can start looking at this in a way that that makes good sense for us. Okay, so let's do Python histograms.py, and this is just going to take a little bit to run. Oh, it is actually going to fail. So I see it. I see exactly why. This is the cat image that we want to throw in here, not IM. And let's run that again. Okay. Oh, interesting. That's actually what I wanted to do, but notice we've got 3 different shapes. They're all actually the same shape, but they're the shapes of the channels, right? So we've got red, we've got green, we've got blue. So now let's go ahead and open up a Jupyter Notebook. It's going to make this a little bit easier to see on the fly. So I'm going to code I'm actually going to code in VS Code, but I'm going to import my functions from histograms.py. So let's go ahead and do that. To Python 3 notebook. And so I'm just gonna make this, back this off a little bit, and let's call this exploring images, and this will be IPYNB, an IPYNB file, and we'll go from there. So the first thing we're going to do is from histograms import, and we're going to just import these functions. So plot image. And what else? We'll import split layers to 3. And we're also going to just, you know, because we're going to be playing around with this, I'm just going to import all of these as well at the top of this file. And that should get us on the right track. Okay. So again, I'm going to import this image. So, why don't I just I'll grab all of this as well. I'll just grab all of this. Yeah. And here's one of the great conveniences of a Jupyter Notebook. You can immediately just see this image, right? You don't have to wait for the strange latency that that I'm experiencing on my computer at the moment, but like in the terminal. And if I grabbed a different cat image, you know, let's grab a different cat. Oh, that does not look like a different cat. That is definitely the same cat. All right. So why don't I just do sub1. All right. There. And that's a different cat, right? So, you know, this still gets us our animals list. And maybe I'll just break this up to make it a little bit nicer to read. Let's do read in image file names. And I'll just grab all of this. Put it there so that we have this in a couple separate operations. So here what we're doing is read in a specific image, or sorry, view a specific image. And and I will get rid of sort of this extra code that we don't really need. Actually, I think all of that is helpful. So we've got the R channel, the G channel, and the B channel, and we can see that they're all the same. Now, if we wanted to, let's say, plot just a single channel, let's see if this works in its present form. I'm not sure that it does, but let's try to just plot R. So there we go. So that's the red channel. This is the green channel. And these are going to be a little bit different, and not that much different given this cat. And maybe it makes sense to look at this with a different cat. Let's look at that gray cat again. Actually, let's look at a different cat altogether. Ooh, not enough variation there. So let's look at... Oh, yeah, this is good. Okay, so you can imagine this in the red channel is going to be really bright if you look at this cloth in the red channel. And it is, right? If we look at the green channel, there's barely any green in there, right? It's just a really dark channel. And if we look at the blue channel, also, there's a little more blue than there is green, but the most prominent color in there is red. And you can see that the value of red, the luminosity value of red, is very high. So this is a good indicator of what we might expect to see in a histogram for this image. So so we've split our layers. Let's extend this a little further. So we split layers to 3. Let's go ahead and let's go ahead and plot a histogram. Why don't we just do that? So let's plot this histogram, and X is our image, and we're still going to pass in a title. So we are going to be able to utilize this in another function in order to compare these images. And that's going to be helpful. It's going to tell us some things about the images we're looking at. So figure axis in plt.subplots, and we're going to set a standard deviation. We're going to get the standard deviation of the image, and we're going to get the mean color value of the image, and I'm going to call that mu underscore, and that's going to be, I'm just using numpy's mean function here, and this is often something that you present with the channel of an image. So we're going to see those. We're also going to go ahead and sort of take X apart. We're going to make it a vector for our purposes here. And I'm going to say that the minimum from this vector is going to be, and notice here, this is X underscore. So I'm not modifying the original X when I do this. So I'm going to say this is going to be the min from X underscore. And I'm going to do the same thing for the max. And then I'm going to describe the range of this, which is just the max minus the min, right? So that's going to give us just some simple you know, parameters of these images. And I'm going to go ahead and set, I'm going to go ahead and create the histogram here. So I'm going to pass in the vector, and I'm going to hopefully make this look kind of nice. So let's do ax.set x label, and we'll set this to make this an F string, and this will be the number of bins, bins with a fit line, and I'm going to plot this with a fit line plotted against the precise values, which we're also going to see. And then we're going to say for the Y label, we're going to do, we're just going to say this is the probability density. We'll just call it that. And that's going to be, I'm not really going to explain that offhand, but I want, when I talk about the histogram of oriented gradients, it's helpful to think of our histogram as a probability density, as a representation of probability density for different values of between 0 and 255 when we're comparing images. And then I'm just going to set a title here, and I'll do it like this. Do an R string. It's going to be, you know what? I can do. I'll do an F string. Yeah, makes sense. So title. Oh no, I know. I want to do an R string because it would be nice to get some LaTeX in here, and this is going to be. Let's do mu, and mu is going to get to 3 decimal places of float, and we're also going to put in a sigma, and this is going to be let's see, the same, except with a little padding on the left. So 0.3f. And I try to avoid using format if I can use an F string, but we're just going to pass in the title, the mu, and sigma here. And then using Seaborn, I'm going to just make it look a little nicer, because Seaborn, it looks nice. It's easy to make things with Seaborn look nice on the fly. And I'm going to go ahead and make a distribution plot using Seaborn, and all of these are going to be superimposed on the current plot. So I believe that is going to do what we want it to do. And I'm also going to import this plot histogram function into this Jupyter Notebook here. All right, so let's, okay, np.ravel, I see my error there. I didn't actually assign it. So let's do that. Try that again. That looks like it worked. And so here we plotted the image. Let's plot the histogram. And hopefully this will work. Plot histogram. And name sigma is not defined. Okay. All right. Name sigma is not defined. Set title. Oh, interesting. I probably didn't name it sigma underscore. Looks like that is the case. Okay. Yep. Yeah. All right. So let's try that again. This is promising. Looks like it's at least trying to work. And it looks like it did work. So I'm going to grab this cat image so that we can look at it next to this histogram. Oh, it looks like I am outputting something I don't want to output there. But this histogram looks reasonable. And what we're seeing is the percentage of values, right? So we would expect, given this image, right, the original image, this is the red channel, and maybe we can just look at this. Well, we don't need a... This red channel is going to have the highest density, and that's what we're seeing. The redness value is going to be highest in this red channel. So what we're seeing is a lot of density up here and down here, right? So if there wasn't as much red, this side of the histogram would be much lower. But notice this is still only 0 to 255. And even though we're seeing this as a grayscale image, this represents the red contribution to the image, if that makes sense. Okay, so I'm gonna fix whatever is going on here. I'm not sure exactly what that is, but it's in the title. What am I doing wrong there? Oh, I think I see it. Okay, so bins. X_300 density is true. So I think I need to set these bins differently. Interesting. Okay, so maybe for now I'm going to just take that out. Not sure how many bins I actually have here. Well, I have 255 here, but I'm missing part of this histogram, like the more narrowed in bins. Okay. You know what? Let's just run that again. Let's see if we get the same results. Okay, that's a little nicer. Still getting something in the X. All right. Something is off in bins right here. I wonder if this ax.hist method changed recently, because I remember it outputting something different. So why don't I just take that out for the moment and go ahead and correct this. And I can troubleshoot that later. Let's see how that does. Okay, this is mostly what we're looking for here. And it's kind of nice to create these histogram bins. I think this is something like somewhere around 60 to 70 bins that we're seeing here, because essentially, like, if you see these white lines behind, and maybe I can blow this up a little bit. If you see these white lines behind, these are the actual the actual values for some of these, and they're just being binned down a little bit. So these are we're considering ranges of values with these bins, as opposed to these specific values. And you find this a lot in images where there'll be a specific color that is very common and it's not spread across. And so it's a little helpful. It's pretty helpful to kind of see this color curve. And this color curve is defined more by the way that the specific color, the range, the bin range that the specific colors fit into, right? Whereas the specific most occurring color, right, looks like it's this, somewhere 253 or something like that for the red channel. So that's why we might do that. And, you can kind of see that here, right? There's a lot. This might actually be 255 that's spread through here. These are really intense reds, and we can see them here. Okay. So this is a mostly working plot. It's the thing with coding on the fly. You can see that for this channel, the mu is, it's kittens, right? So the mu is 169, and that's, with a standard deviation of 64.810. So that kind of makes sense, right? You can kind of see the spread around 169. Makes sense. All right. Now, if we were to look at the green channel, this is going to look different, right? And it should look different. So notice there's much lower values for green, and that's what we would expect. And if I look at it here, we can see that, right? We've got this very common value in here, somewhere in the 30s probably. So I'll go ahead and sync this up to GitHub so that you can grab it if you want. And we're going to continue to code a little something else so that we can see, we can do these image comparisons kind of on the fly. And I think that's going to be helpful. All right, so we wrote a plot histogram function, but now we're going to write a plot histograms function. Don't know why Bash is taking so long to load. The computer's been a little strange today. All right, so let's write the plot histograms function. Again, we're going to give it a title. And I'm going to set a flag, image is false. Okay, there we go. And let's just push all of this up. All right. These are terrible commit messages, by the way. I usually write really good commit messages, but given that we're streaming, I'm writing poor commit messages because I just have this little git adder script that pushes everything up. So it's not a great practice. I'm not trying to encourage that practice, but the time it takes to type out these commits every time, I'm just avoiding that. Okay, so when we plot these histograms, we're going to plot the images next to the histograms, and if images is set to false, we'll only plot the histograms. And then we're going to plot a grayscale channel, and we're actually going to plot an averaged image channel, and there's a reason for this. So maybe before we write this, I'm going to write something called average image. And this is going to be, let's go ahead and put this above the plotting functions. And we'll do this, so def average image, and we're going to pass in an image. And what we're going to do here is, let's go ahead and split out the layers. And I'm going to do this sort of agnostic of the, if this image is not RGB, if it's HSV or some other encoding, color encoding, but it's still 3 layers. This should be fine. So I'm going to go ahead and do this like this. So I'm going to split these layers to 3, right? And we're going to go ahead and pass in the image. So it's convenient. We already have that function written. And I'm going to average all the layer values. So I'm going, since there's 3 of them, I'm going to go ahead and do a third of each, right? And I'm going to go ahead and, so I'm going to do this 3 times. Go ahead and do that. And we're going to do this with layers 1, 2, and 3. And now when I do this, it's going to be in the form of a float, right? But I want to maintain this as being an integer. So I'm going to go ahead and convert it to an integer in this return line. So I'm going to take that averaged, call it averaged, and I'm going to return it as type int. Okay, so this is 1/3 of the red value plus 1/3 of the green value plus 1/3 of the blue value. And that's going to be returned for each pixel. So we're taking the image, we're literally averaging it. And as you can imagine, that's going to turn it into something like grayscale. Now, oh, looks like I have an error here. Nope. The thing about grayscale, this is different actually than grayscale. Grayscale tends to weight certain values more than others. Actually, I still have an error here. What is going on? Oh, right. 1/3, not 1.3 point. That makes a lot of sense. Okay. All right. And there are times where an average image is what you're actually wanting, not a grayscale image. Grayscale images are optimized for being viewable, and an averaged image is literally just the average of each channel for each pixel. So we're also going to, when we plot these histograms, we're going to plot 4 things. We're going to plot the grayscale image, we're going to plot the averaged image, we're going to plot the red, green, and blue channel. So let's go ahead and plot all of these. So I'm going to get a grayscale image, and I imported from up here this RGB to gray. So we're just going to use that. So this is going to be the RGB to gray of the image. And we're going to convert this to, we're going to take that gray image, and this actually returns a value between 0 and 1. So you can represent an image between 0 and 255, or between 0 and 1. Those are perfectly acceptable, 2 different perfectly acceptable ways to represent an RGB image. But we want to keep this in a range of 255. So that's what we're doing here. And yeah, this grayscale image, these will be floats, but it doesn't really matter, right? 255 times 0.6 is going to give some value that has the float, but has a float value on the end. But when matplotlib interprets this, it's basically throwing away the float. The float is not contributing. So we're not going to worry about converting it any more than that. So gray gets 255 times gray, and then we're going to process this just a little bit more. And let's say gray, yeah, actually let's convert this to ints, just in case there is some sort of error that we hit, and just for the sake of best practices anyway. Okay, so that's our conversion, and maybe we can just put this into its own function, def convert to grayscale. And we're going to put an image in there, and we'll go ahead and do all of this just up there. And instead of, so this could be more compact, but I think it's nice to see the steps there. And then we're going to get convert to grayscale of that image. And so that's our gray version. And our averaged image, this is easy enough. We already wrote this function. averaged image is going to get the average of, I think that's what we named it. Yep, that's what we named it. So average image of IM. And and then we just need each of the individual layers, right? So let's do R, comma, G, comma, B. That's going to get split layers to 3 of IM. And now we can go ahead and start our plotting, right? So I'm going to say if images is true, right? If we want to show the images, then we're going to plot the gray image, and I'm just going to say grayscale luminance. And often when you think of a grayscale image, you're actually looking at what we think of as the luminance values. And that's sort of like the, you can think of it as the saturation of light. So these are the weighted channels, weighted by the grayscale function that we use, the RGB to gray. And then we can go ahead and plot the histogram of gray. And this is going to be, so luminosity histogram, and we're just going to call it that. So I'll make this an F string, and we'll pass in the title. And let's just do this. Is that how we want to do that? Yeah, we'll just go with that. And we can take the same. I'm just going to do this over and over again. I'll do it 4 times. And we're just going to do this for each of the different. So this is gray, this one's averaged image. Then we've got R. Oh, I need one more. I'm actually doing this 5 times. This is G. And we're going to do blue. Okay. And we just need to change these titles. So this is going to be this is the grayscale luminance and luminosity histogram. This is the 3 channels averaged. So this is 3 channels. Do this. Channels averaged to 1 channel. Just do that. And call this the averaged histogram. And then this is going to be our red channel. And we can call this the red's histogram. This is going to be the green's channel. And we'll call this the green's histogram. This is going to be the blue channel. And just to be consistent, we'll call this the blue's histogram. Okay. So theoretically, this will work. I'm sure there's errors in here, but let's find out. Let's just grab this and jump over to that Jupyter Notebook and hope for the best. Actually, we need to import this first before we hope for anything. We need plot histograms. I don't think we need anything else from there because all of this is going to be handled. Okay, so let's plot histograms for this image, and let's see how it goes. So this is, why don't I do this? I'll say cat image. yeah, let's do, I'm going to say choice. I'm just going to make this so that I can change these on the fly without having to change them in more than one places. So let's read in the choice. Oh, yep. And plotting image of the choice. So, yeah, that's fine. Yeah, that'll be fine. And there's our original image. Here's our, this is our greens channel. I'm actually going to just delete this cell. And yeah, I think that's fine. And let's just leave this as only plotting the reds channel. But then here, we're going to plot image title, and images is going to equal true. So why don't we do that? So plot histograms is going to be, what was it? It was cat image, and then choice, and something equals true. That was images equals true. So cross your fingers, and of course that didn't work. All right, too many values to unpack. Oh, that absolutely makes sense. Layer 1, layer 2. Okay. Why is that? Layer 1, layer 2. We need a layer 3. This is what happens when you do not test your functions when you write them, and you just assume they're going to do okay. Okay. So let's try that again. Okay. That's our grayscale. And we're going to get a histogram shortly. So this is our grayscale histogram. And we're going to get a few more of these. I'm just going to zoom out. So notice that our grayscale is actually different than our averaged image. And this is a common thing, that your grayscale image will be different from your averaged image. So there's our averaged image. So these are very, very slightly different. It's not that noticeable. Most of where you're noticing it is in these reds, right? And you can imagine why. The average, the grayscale is not allowing these to contribute quite as much as they're actually contributing in the original image, right? That is some intense red. And this is how the RGB to gray function does it. This is a pure average, the 1/3 contribution of each channel. And so, but at the end of the day, these plots don't look that different. If we look at this histogram versus this histogram, they're not that different. And this is totally fine. But they are really close. Yeah, these are very, very close, but they're not the same. And we can see that. So now we can look at the red channel, and of course, red is highly contributing. We can look at just gonna grab these, and we can look at them. We can look at the the greens channel. And we can look at the blues channel. And I didn't grab the values for mu and sigma here, but I think we can sort of get an idea of what those, roughly where those are. So yeah, looking at these, we can see that red is highly contributing. Green and blue are not as highly contributing. And that makes a lot of sense given the image that we were looking at. Yeah. So if you have histograms, you can actually start to pretty effectively approach things like object and face recognition. And I'm not going to code any of that out today. I really just wanted to show you how to read in and plot some histograms of cats. That's the main goal. I might show you another, couple things about preprocessing. But I kind of want to point you at this paper, this histograms of oriented gradients for human detection. This is an object detection approach that uses histograms. And through using histograms, you get sort of a sense of silhouettes of things, and you can detect things, right? So this is one of the earlier pedestrian detection algorithms. And it's important to know where the technologies you're using now, where those came from. And even though this is old, it's still useful. You might imagine that if you are feature engineering on a series of images, you might pass into a network not only the channels of the image, you might pass in a histogram of the channels or a histogram of some other set of features, like let's say luminosity or some abstractive luminosity such as lightness. Those are things that you might use as inputs to a neural net, and those would be sort of feature engineering in your data set in that case. And those approaches can include things like histograms. That is not uncommon. Histograms are nice because in this case it's 0 to 255, right? You take this massive data set, and you can because you've made it a probability density, right? It doesn't matter how big each image is. Like, you could have different sized images, and you're always dealing with an area of 1, as opposed to trying to compare images that are different sizes, where you would have to resize the image in some way in order to effectively compare them. So yeah, this can be a really nice either naive approach or supplemental piece of information to pass into a network. So that's some thought about this histograms of oriented gradients. And I'll throw this into the description under further reading, if that's something you would like to do. So that's histograms of oriented gradients. And I'll also put it into the chat. All right. So I'm going to go ahead and do another little pre-processing thing to just demonstrate this. So there is this idea of scaling an image. And this is something that you do pretty often because you get images of different sizes. And let's say you're trying to do some kind of detection of objects across a whole bunch of images, or you're trying to train a network to be able to detect certain objects across a whole bunch of images. You might scale all your images so that they are of similar size, and that might skew them to some degree, but it might be necessary. You might also trim the images, right? That's another way forward. You can imagine trimming is just dropping, taking the center of the image or passing a window over an image, like let's say turning a single image into 4 images, that kind of thing. But scaling is a pretty good way forward for a few reasons. When you are building your network, often you don't want to use giant images to try to make something happen, because the computational overhead is just going to be so much higher, right? Like, having a small image, let's say 30 pixels by 30 pixels, is going to be much, much easier to wrangle in than a 540 by 480 or much larger 1020 pixel image. you're going to be trying to build something, and you're trying to build it with the the heaviest hammer, and the you're just trying to build it with you're going to continually have lag, right, in what you're doing if you take that approach. So what we'll do now is we'll just rescale an image. This is one of those things that you're going to find really, really important. And let's just say rescaling images. I'm going to use CV2 here, and I'm just going to import it here. So I'm going to import CV2. Hopefully I actually have it installed. Good. It's a little afraid for a second there. And let's call this, what was this? Cat image, right? So let's grab that. Let's do cat image resized, and this is just going to be cv2.resize of the cat image, and I'm gonna do 32 by 32. So I'm making it square, and I'm dropping a lot of things, and I'm going to use cubic interpolation, which you'll see what this looks like in just a second. So enter cubic, and actually before we do that, why don't we look at the shape, right? So this is cat image dot shape. That's 150 by 199. And after we do this, let's look at the shape again. So cat image dot shape, and resized that shape, and it's 32 by 32. Not a big surprise, just it's always good to verify for yourself what's happening. And then let's go ahead and plot the image of cat image resized. And I'll fix these titles later. Oh, yeah, maybe I will. We'll find out. Okay, so I'll grab the original image up here, and we'll just look at them side by side. And when you think about bins in histograms, this is not that different of a concept, right? We've effectively binned a bunch of colors here. And if we plot the histogram of this, and why don't we go ahead and do that? Why don't we just plot histogram of the image resized, and let's compare it to the other histogram. Actually, should we do a specific channel? Yes, we should. Let's plot histograms of cat image resized, and do choice, and we'll set images to true. And this should run a little bit faster than the other one, and it does. So, a lot of these will likely be the same. So let's grab that luminance channel first, that grayscale luminance channel. That's here. And this time I will grab our I'll grab our other values, and let's compare this to what we're seeing here. I mean, notice this isn't really different. Our mu is very slightly different, and our sigma is very slightly different. That's it. That's it. But at the end of the day, this curve, the original curve has a little bit more form, a little bit more variance in it, on a micro level, right? Like we jump up a little bit here and there, and this is a little smoother. So you can imagine that this approach smooths your, it smooths your line for your histogram. And yeah, that's, this is just a simple pre-processing technique that you use all the time in order to make a data set that will run faster on your network. And it's really helpful. So, when people say rescaling, you can use cv2.resize to do that. yeah, and all the rest of these histograms, you know, if you want to go through this and verify it for yourself, these histograms basically end up looking the same. Okay, so yeah, that's it for today. I'm going to clean up a little bit of this code. I'm going to try to fix that bins issue that I was having, and I'm going to make this make these titles a little less obnoxious. Right? We don't need the entire file path in here. We could just do yeah, we do not need the entire file path. I'll just say that. And I'll go ahead and push this up to GitHub. If you want to play around with it, there's a few extra cat images in here. Obviously, you don't need to use cat images. You can use any images. This should read in a JPEG, a PNG. It might have trouble with a GIF or GIF, however you care to pronounce it, although I have a hard time saying the word GIF. Even though I know that's what it's supposed to be called. But it probably won't handle GIFs very well. So if it's a GIF, you might need to convert it into a PNG or a JPEG or something like that in order to do that. But yeah, if you have any questions, feel free to reach out to me either on Slack or comment. And if you see something weird or buggy in my code, let me know, and I'll do my best to make it universal for people. Obviously, this is using a Mac, but this code, and you might need to do something a little different on a Windows machine. That's possible, but this code should work on a Linux machine or on a Mac, and I think it will work on a Windows machine. I can't say for sure offhand, but once you get the image read in, everything else is the same, and that should be platform agnostic. So yeah, thanks so much, and take care. And yeah, I'll be back next week with, I think, some more image processing. I think I'm going to stick with image processing for a couple weeks. I think there's some interesting and exciting things in that space. And yeah, I just want to open up and explore some of those things with you so that you can bring those into the DSI or into your own studies, whatever that might be, and apply them, because they're within reach, right? This isn't that hard to do, and I think it's really fun, and yeah, gets you some good results. Okay, thanks so much.